Okay, let's unpack this. For the last little while, we have been diving pretty deep into the world of software, really playing around with MiniPy.
Right.
We've established how to write programs, what functions are computable within that whole framework, and basically laid down the logical ground rules for programming.
Hmm.
But today, we're shifting our focus
Okay.
completely.
What agree.
We are moving from the logic of the code of the software to the logic of the machine itself, the theoretical hardware.
That's exactly right. Our previous discussions were all about defining computability through the lens of programming. The question was always, can we write a sequence of instructions, increment, decrement, while loops, to solve some problem X?
Yeah.
Now we have to turn the mirror onto the theoretical hardware and ask the inverse question, which is just as fundamental.
Which is?
Can a physical machine, regardless of how fast it is or how much memory it has, can it actually compute more than the most minimal structured program we can come up with?
That feels like a huge, almost philosophical question. It gets right to the core of physical constraints versus abstract logic.
It does.
Are the limits of what we can compute defined by the programmer's cleverness in writing an algorithm or by the actual circuitry and physics of the machine running it?
Well, to answer that, we have to just abandon all the noise of modern technology.
What do you mean by noise?
The clock speeds, the gigabytes of RAM, the complicated bus systems, all of it. We need to get back to first principles.
Yeah.
So our mission today is to understand the absolute simplest, most elegant, and really the most minimal model of a computer that still has the full computational power of the fastest supercomputer on Earth.
And this model, of course, is the profound invention of Alan Turing.
The Turing machine.
So the ultimate goal here, then, is to prove this staggering claim that the Turing machine, a device built on basically nothing but an infinite tape and a simple little reading head, can simulate any modern supercomputer. Or, and this is the crucial part for our discussion, any MiniPy program.
Exactly. If we can prove that this theoretical hardware model and our software model are conceptually equivalent, that they define the exact same boundary of what is and isn't solvable, then we've defined the logical limit of computation itself.
And that's the grand synthesis.
That is the grand synthesis of the Church-Turing thesis. We came at computability from the software side with MiniPy. Now we have to check that the most minimal possible hardware can get the exact same results. It's a journey that shows us that really most of the complexity in computation is, well, it's just an illusion. It's a matter of engineering efficiency, not logical necessity.
To really appreciate the elegant simplicity of the Turing machine, we have to start with what it is not.
Good starting point.
If you look inside any computer today, I don't care if it's the chip in your phone or some massive server farm, you are dealing with the classic but inherently complex von Neumann architecture.
Right. This architecture is the foundation of all digital computing, but it's complex for a reason. It's designed for physical efficiency, for speed. You have all these specialized components, input and output units, the I/O to deal with the outside world. You have the memory unit for storage. And they all talk to each other through a high-speed bus system.
And then there's the brain of the operation, the CPU.
Right, and even the CPU is split into two specialized subunits. You have the reckon work, or the arithmetic logic unit, the ALU, which does all the math.
Addition, subtraction, all that.
And then you have the store to work, or the control unit, which is like a traffic cop, regulating the flow of data and instructions.
Okay, that sounds like a well-oiled machine, but you're saying that for a theoretical analysis, it's just too messy.
Way too messy. It introduces all these physical constraints like how fast the bus is or how much RAM you have, and those things distract us from the logical constraints we're actually trying to find.
We're trying to find the limits of logic, not the limits of, say, Intel's manufacturing process.
Precisely. So we have to strip this complex machine down to its absolute essential necessary core. Let's start that process of abstraction. Let's shed all the unnecessary physical baggage.
What's the first component we can lose without losing any actual computational power?
The bus system.
The bus. Why?
It's absolutely necessary for a real-world computer to get data quickly from RAM to the CPU, but it's completely irrelevant for the pure act of calculation. It's just a transport mechanism, doesn't perform the computation itself.
So for theory, we can just assume the data gets where it needs to go instantly.
Exactly. So goodbye, high-speed bus. We don't need you for this.
Okay, what's next? The I/O and the memory. In a modern machine, those are very different things. Memory is the RAM chips. I/O is my screen and my keyboard.
They're physically distinct, yes, but logically, what do?
They store information.
They store information. The input is just data that gets written to memory. And the output is just the final data structure you read from that same memory. So logically, we can just consolidate them into a single conceptual storage space.
Okay, we're down to just storage and a processor. Now comes the really radical non-physical leap. Abstraction 3, right? Infinite memory.
This step is absolutely crucial. It's what defines the theoretical power of the Turing machine.
Why? Why is that so important?
Well, think about it. If we kept the finite RAM of a real computer, any failure to compute a function could just be blamed on running out of space.
The program crashed because I only have 16 gigs of RAM.
Exactly. It becomes a resource failure. But we don't want to find the limits of a physical machine. We want to find the limits of logic itself. By assuming we have infinite limitless storage, we make sure that if a function can't be computed, it's because of a flaw in the logic, a flaw in the algorithm, not because we ran out of tape.
So by going infinite, we're really defining the absolute theoretical maximum potential of any machine. Okay, so now let's simplify the structure of that storage. RAM is complicated. It's got addresses, memory management, pointers.
Far too complicated for a minimal model, so we replace it with an infinitely long one-dimensional tape.
Like a roll of paper.
Like a roll of paper that extends forever in both directions. And this tape is divided up into discrete little cells. In each cell, you can store one simple unit of information. One symbol.
A 0, 1, an A, a hash mark, whatever.
Becoming you define for your alphabet.
So we've boiled the entire data storage system down to an infinite chalkboard. What about the processing unit? The brain, the complex CPU?
We reduced that complex dual-purpose CPU with its specialized math unit and its control unit down to a single, simple, and this is key, a finite control unit.
Okay.
This unit is the minimal logic processor. It can only do 4 things.
4 things.
1, read the symbol that's on the tape under its head. 2, potentially write a new symbol in that same spot. 3, change its own internal state, its finite memory. And 4, move one cell to the left or one cell to the right. That's it.
So why is it so important that the control unit, the brain, be finite even if the tape is infinite?
Because if the brain were infinite, if it could remember an unlimited number of instructions or states, it would essentially be the solution to every problem already.
It wouldn't be computing anything. It would just know.
It would just know. Any real machine, or even a theoretical one, has to operate based on a finite set of rules. The finiteness of the control unit is what makes the Turing machine an accurate model of an algorithm being executed by a machine.
The final result of all this radical simplification is just 2 things. The infinitely long storage tape and this read-write head controlled by a simple finite logic unit.
That is the Turing machine, named after Alan Turing. And its genius lies in that extreme simplicity, which, as we're about to show, still holds all the computational power of the most complex machine you can imagine.
Its simplicity is its strength.
Its mathematical strength, yes.
Yeah.
It lets us formally analyze computation without any of those physical distractions.
So we've introduced the TM in an intuitive way, but to really understand its power and, mathematically connect it back to our MiniPy programs, we need the formal definition.
This is where we have to get precise.
This is where we shift to the syntax and the structure.
Exactly. We define the Turing machine, or TM, as a 7-tuple. It's just a mathematical list of 7 components that fully describes the machine's architecture and everything it could possibly do. That's definition 1.5.
A 7-tuple. Okay, let's break that list down, but conversationally, let's ground each piece in what it actually does.
Okay. First, the finite set of states, which we call $2.
This is the internal memory of the control unit, right? The brain's current status.
Exactly. It's a finite number of possible internal configurations like I'm ready to read, or I'm currently in the copying phase, or I'm looking for the end of the word.
Got it. Second,
the input alphabet, or a sigma van. This just defines the characters that are allowed in the starting input word. So if your machine only accepts binary numbers, sigma mater might just be the set containing 0 and 1.
It's the set of legal characters for the problem we're trying to solve.
That's a great way to put it. Third is the tape alphabet, or gamma.
Okay, this is where it gets interesting, you said.
Yes, because gamma is everything that's allowed to be on the tape during the calculation. It has to contain the input alphabet, sigma, of course, but it can also include any temporary or special scratch symbols the machine needs for its internal bookkeeping.
So wait, sigma is like the language the user speaks, and gamma is the machine's full internal toolkit, its jargon. Why the distinction?
It's absolutely vital. We'll see this with the word doubling example later. If you only had the input alphabet, how could you mark a character as already copied? You can't.
Oh.
You need special symbols, like an $all or a BALO, that exist purely to manage the control flow, but which are never part of the original input or the final output. Gamma is that expanded set that includes these crucial markers.
Makes sense. What's number 4?
The blank symbol. We usually write it as a square, quant barme, or just VO dollars. This is the special symbol that marks the infinitely empty part of the tape. It's what the machine reads when it moves beyond the input you gave it. And it's a mandatory part of Gamma.
Number 5.
The start state,
Yeah.
dollars. Pretty simple. It's where the calculation always begins.
Mm-hmm.
You need that for reproducible results.
6.
The set of end states, key dollars. If the
Yeah.
machine ever enters a state that's in this set, the computation halts successfully. If it halts in a state that's not in Q, it's considered an error or maybe just a non-accepting halt.
And the 7th, the most critical piece, the element that holds the entire logic together. The transition function.
Absolutely. The delta is the heart of the machine. It is the machine's code.
Okay.
It defines the machine's behavior for every single possible situation. It takes 2 inputs, the current state the machine is in and the symbol it just read from the tape. And based on just those 2 things, it dictates a unique next move.
3 things, right?
3 things. A new state to go into, a symbol to write on the tape, and a movement direction left, right, or neutral.
So if I'm in state, say, a 1s, then I read a 1 on the tape, the transition function might tell me, okay, write in Newwood, switch to statary, and move to the right.
That's a perfect example of a single instruction. The graphical way we draw these, with states as circles and transitions as labeled arrows, it shows you that all the control flow, all the sequencing and branching is handled entirely through these mandated state changes. There's no central OS. The transition function is the operating system.
So that's the blueprint. Now, how does it actually run the semantics? This requires understanding the concept of a configuration.
A configuration is basically a full instantaneous snapshot of the entire system at one moment in time.
A freeze frame.
A freeze frame, exactly. And since the tape is infinite, we can't write down the whole thing, so we define the configuration using this word structure. 10Q V dollars.
Let's break down a Dory QV vol very slowly, because I think this is where it can get a little confusing.
Sure. So all the content on the tape to the left of the head. Doors is the content on the tape starting at the head's position and going to the right. And these strings and dowels are finite. They just need to be long enough to include all the non-blank symbols.
And the dollars, the state, is just jammed right in the middle.
Precisely. The state dollar is physically embedded in the middle of that word, 1QV dollars. And the reason is that the state dollar acts as the marker. It's the cursor. It tells us not just what the machine is thinking, but where it is looking.
Let's use the example from the source. 01 #1 blank 2J02 $10. How do I read that?
Okay, that tells you 3 things. 1, the machine is currently in state 2 shell 22. 2, the tape content to the left of the head is 01 #1 blank. And 3, the head is currently positioned on the very first character of the string 10.
So it's reading a 1.
It's reading a 1. The state $2 literally sits immediately to the left of the symbol the head is currently processing. It is a brilliant piece of symbolic abstraction. It combines the machine's location and its mentality into a single representation.
Okay, that makes sense. Now let's look at the calculation relation definition of 1.6, which is just a single step. How does the machine move from one configuration $$ to the next $2?
It all depends on the movement that Telltale tells it to make. Let's say we have a starting configuration, maybe 1 ray B, VV fifth.
So the head is reading the symbol by $, and we're in state dollar, and the symbol is immediately to the left of where the head is.
Perfect. So first case, a neutral move. And let's say Delta says right syllable move in, go to state dollar. In that case, only the character changes to syllable and the state money changes to seller. The new configuration is 1 I key C view A. The head stayed put.
The state just swapped out that didn't move.
Exactly. Now, a right move R. If Delta says right seller move R, go to state dollars. The machine writes $2 over dollars. But then, since it moves to seller, the new state dollar shifts 1 position to the right. It lands behind the newly written seller. The configuration becomes $1 C key via.
So the state marker has basically hopped over the character it just wrote, moving 1 spot to the right.
That's it. Now for the trickier one, the left move.
Okay.
If the seller says right seller move L, go to state dollars. The machine still writes $2, but this time the state dollar shifts 1 position to the left. It lands before the character O, which was previously to its left. The new configuration is 1IAC v AUA.
Whoa, okay. So when it moves left, the character that was just behind the head is now under the head. The state dollars essentially jumps over $1 to get to its new spot.
Yes. That complex shifting of the state dollar within the configuration word is how we model a physical head moving across a physical tape. It's really
And
clever.
that defines the whole process.
It does. If you string these single steps together, you get a reshnum or a computation. It starts at the initial configuration dollar, followed by the input word $2. And it just keeps going until it lands in a configuration where the state is one of the end states, in Q dollars. And critically, it has to do this in a finite number of steps.
We have to keep emphasizing that finite number of steps.
We do, because that leads directly to how we define the function that the machine calculates. The function 5mxy is only defined if the machine halts successfully. If it doesn't halt, if it runs forever in an infinite loop, the function is simply not defined for that input, $6.
And that's the mathematical hook. That's how unsolvable problems are defined. An input that leads to an infinite runtime.
Precisely.
Let's ground all this formalism with a concrete example. The word doubling machine.
Perfect example. The goal is to take an input word dollars and produce $2. So if you input ab, the output should be abab.
Something we do in a high-level language with something like string, string plus string. How does this simple machine handle it?
This is a perfect demonstration of how complexity is managed by simple state changes. We need control flow, we need marking, we need memory management. And since the control unit's memory, Q's lar, is finite, we have to use the tape itself as a scratch pad.
And this is where the extended tape alphabet gamma comes in.
This is where it's essential. We use our marked characters, A-baller and baller.
I can see why the marks are crucial now. If the machine just reads an A, it has no way of knowing if that A has already been copied or not. The mark is the temporary memory of its status.
Exactly. So the overall strategy is a systematic sweep. First, find and mark. It starts at $2, scans right until it finds the first unmarked character, say an A. It transitions to a state, maybe writes A, and moves right.
Okay, it's marked the A.
Then step 2, scan to end. It enters a state, let's call it the canned, that just has one job. Relentlessly move right, ignoring everything, until it hits the first blank symbol.
It's looking for the end of the current word.
Right. Step 3, write and return. When it reads that blank, it transitions to a state, writes the original A character, and then transitions into a new state. And step 4, scan back. This new state's job is to move left until it finds the marked character, that A, and then it transitions back to the very beginning to $2 to repeat the whole cycle with the next unmarked character.
Hang on a second. How does the machine remember that the character it found and marked was an A when it gets all the way to the end of the tape to write it? The control unit is finite. It can't just hold A in its memory.
This is the genius of the state transitions. When the machine reads A in step 1 and transitions, it doesn't just go to a state, it transitions to a state specific to that character.
Okay.
Let's say the specific character A is encoded in the state itself.
Oh.
So when that specific state eventually hits the blank symbol, the transition function is like a lookup table. It says, if you're in state write 4 and you see a blank, then you must write an A. The memory was stored in the state the whole time.
The finite set of states, Q, serves to hold not just the current instruction, but also the temporary data that's in transit.
Precisely. And once all the original characters are marked and copied, the machine enters a final cleanup phase. It just scans the whole word one last time, changing every F bucket to A-word and every ball back to B-word, and then finally halts in an end state. This complex task is just a fixed, finite set of rules executed sequentially on an infinite tape.
Okay, so we've established these two powerful but on the surface very different models of computation. We have MiniPy, which is a structured software model that works on natural numbers, on MathBBN.
Right.
And we have the Turing machine, which is this minimalist hardware model that works on strings of symbols on Sigma and Eller.
And the Church-Turing thesis claims these two systems are, for all intents and purposes, functionally identical.
They can compute the exact same set of functions.
The Turing computable functions. And this is, you could argue, the most important foundational theorem in all of computer science. To prove it, we have to show that we can bridge the gap in both directions.
Let's start with the language barrier. MiniPy uses numbers, TMs use strings. We have to standardize the input.
We have to standardize through codification. It's simple enough. We just code every natural number, no to Lawler, that MiniPy uses as its binary string representation. Bit of a nut.
But what if a MiniPy function has multiple inputs, like 6 by $, by 2 by 3, 3? The TM only has one tape.
That's where the idea of a multi-track Turing machine comes in. Instead of trying to use speckle separators like a hash sign, which would make navigating the tape really complicated, we just conceptualize the single tape as having multiple parallel tracks.
Like lanes on a highway.
Exactly. If a MiniPy function has, say, dollar variables, the TM will have dollar tracks. And the read-write head reads and writes simultaneously across all dollar tracks at whatever position it's at. Each track holds the binary value of one variable.
With that setup, we get to theorem 1.9. TMs are as powerful as MiniPy. The claim is that for any function you can compute with a MiniPy program, a Turing machine exists that can compute the exact same function.
And this demonstrates that the simple tape and head are sufficient for all structured software logic. We proved this by showing how to build a Turing machine, let's call it MPy-T, that can flawlessly simulate any possible MiniPy program. Pay dollars.
And we do that by building TM routines for the fundamental operations.
Yes, the building blocks.
Let's start with the atomic operations. An increment xi plus equals 1. In a modern CPU, that is a single instantaneous hardware operation in the ALU. What does the TM have to do?
It's significantly more complicated for the minimal TM. The machine has to move its head to track of dollars, find the end of the binary string, and then execute a whole binary increment subroutine.
A subroutine?
Yes. It has a scan from right to left. If it sees a 0 mod, it flips it to a 1 and it's done. But it sees a 1 and it has to flip it to a 0 and then move left to process the carry bit.
It's a ripple effect.
The ripple effect. And if it carries all the way to the end and runs off the left side of the number, it has to append a 1 to the beginning, expanding the word.
Wait a minute. You're telling me that a single, simple software instruction like xe plus equal 1 requires a dedicated multi-state subroutine just to handle the ripple of a carry bit across the tape. That sounds incredibly inefficient.
It is incredibly inefficient in a physical sense, but we don't care about time. Theoretically, what matters is that the TM can do it, and that it halts eventually. The fact that it can model the carry ripple, the fundamental process of arithmetic, proves that it's arithmetically powerful enough to match MiniPy.
Okay, so what about decrement equals 1?
Yeah, similar story, similar complexity. It's a modified binary subtraction on track, $1. But since MiniPy only works with non-negative integers, the TM also has to implement that non-negative constraint.
Meaning if the number is already 0, it has to do nothing.
Right. It has to check first. If it sees only zeros, it just halts the subroutine. If the value is non-zero, then it executes the subtraction, which involves finding the rightmost one bren, flipping it to a 0, and then flipping all the subsequent zeros to 1s. Again, a systematic scan and manipulation, all defined by state transitions.
So we have routines for the atoms. What about sequencing? Putting programs one after another.
Sequencing is actually the easiest part. That's lemma 1.10. If you have two programs, peoples and one in peoples, will run by machines, MEP and one in peeler, you just stitch them together.
Oh.
You take the end state of the first machine, MP and on, and you just redesignate it as the start state of the second machine, MP2. So the moment MP finishes, MP it automatically starts, using the output of the first machine as its input. It perfectly mimics executing MP or then TP21.
We've built up everything except the defining control structure of MiniPy, the while loop.
The crucial step.
How does a machine built on linear movement and finite states simulate the complex control of while y is not 0, do p?
This is where you can really see the synthesis of hardware and software logic. Yeah. We transform that loop structure into a coordinated dance of state transitions that allows for iteration based on a condition.
Let's break down the simulation into its functional phases.
Okay. Phase 1, the condition check. This is the while HE 0 part. The TM starts at a special loop entry state. Let's call it ucheck $. Its job is to scan track IJail, which holds the binary for $6.
And it's looking for a 1.
It's looking for a single 1. If it scans the whole number and finds only zeros, or it's blank, that means $6 is 0. The loop condition is false. The machine then immediately transitions to the final halt state, completely bypassing the loop body.
And if it finds a 1?
If it finds even one condition is true. The machine then transitions from check into the next phase.
Phase 2, execution, the do p part.
Right. If the condition was true, the machine starts running the dedicated submachine for the loop body, the MEP, which we already know how to build. So MP executes the body, maybe incrementing or decrementing other variables on other tracks.
And when lemby is done, it can't just halt. That would break the loop.
Exactly. This is phase 3, the loop back. The very final transition of the loop body machine 1IB is specifically designed to do one thing. Transition the TM right back to the initial checking state, check time.
So it forces the machine back to the top of the loop to check the condition on track, all over again.
Yes.
And this repeating cycle check, then execute, then loop back, is the perfect, if mechanical, hardware simulation of the while loop.
It is. We have taken the most complex control structure in our high-level programming language and shown that it is completely reducible to a finite sequence of simple state transitions on our minimal hardware model.
And that officially proves Theorem 1.9. The Turing machine can do everything that is mini-pi computable. It is computationally sufficient.
That's right.
That is a remarkable realization. It means that whether you think about computation as a set of structured instructions, like software, or as mechanical, state-based manipulation, like hardware, you're talking about the exact same fundamental mathematical capability. Okay, we've established the Turing machine's power by showing it can simulate our software model, mini-pi. Now we have to flip the tables. Can mini-pi, our software model, simulate the Turing machine?
And this leads to the second, and I would argue even more astounding, pillar of the Church-Turing thesis. This is the foundational concept behind all general-purpose computing.
Theorem 1.11, the universal program.
Yes.
The claim is that there exists a single mini-pi program that is capable of computing all Turing computable functions. Not just a program that can do many things, a program that can emulate any other program.
This single remarkable mini-pi program acts as a TM interpreter. You can think of it like a virtual operating system that's written in mini-pi. It doesn't solve one specific problem, it solves the problem of solving problems.
And for it to work, this universal program needs two key pieces of information as its input, which I assume we also have to code up as binary strings.
We do. First, it needs the coded description of a specific Turing machine, null or dollars. We have to encode the entire 7-tuple, the states, the alphabet, and most critically, the entire transition function, delta vet.
So we turn the blueprint of machine dollars into a long binary string. It's the instruction manual.
Right. And second, it needs the specific input word, dollars, that the machine dollar is supposed to run on.
So the mini-pi program takes this coded machine description and the input word, and then it just starts simulating Noller's behavior step by step. It meticulously follows all those calculation relation rules we talked about, the movement of the Deller QV configuration.
Exactly. The mini-pi program uses its own variables to keep track of mini-dollar's current state, the current tape content, and the transition function. In every single iteration of its main while loop, the mini-pi program performs a lookup. It asks, if the machine I'm simulating is in state X and reads symbol Y, what should the tape and the state change to?
And then it just updates its own variables to reflect the next configuration of the simulated TM.
Over and over again. If the simulation halts, meaning the TM enters one of its end states, the mini-pi program outputs the result. If the TM would have entered an infinite loop, then the mini-pi program itself enters an infinite loop, correctly mirroring the behavior of the original machine.
So the ability to write this single master interpreter confirms that mini-pi is powerful enough to handle every operation of the Turing machine.
And this concept is then generalized in Theorem 1.12, the universal machine, which we can just call dollar.
And whether we're talking about our software model, mini-pi, or our hardware model, the TM, there exists a universal instance, a dollar.
Formally, the function fViena, the universal machine running machine dollar on input dollars, is exactly equal to fViena. The universal machine is the ultimate tool.
And this is where the theory just smacks right into physical reality, isn't it?
This is where it hits the road. Every single modern computer is a physical realization of the universal machine. It is the hardware that is capable of simulating any arbitrary machine, like your operating system, a word processor, a video game, simply by reading the software's instructions, which are provided to it as data.
And this brings us to the monumental takeaway, the philosophical and practical insight. Code is data.
That phrase completely revolutionized the world. Before this concept, a machine was purpose-built for one job, a calculator calculated, a loom wove. If you wanted to do something else, you had to physically get in there and rewire the circuitry.
Right.
But John von Neumann, who was heavily influenced by Turing, implemented this concept, the stored program architecture.
Meaning the instructions are stored in the very same memory space as the data they're supposed to manipulate. They're treated identically.
Yes. The physical hardware of your laptop is fixed, just like the tape and read-write head of the universal TM. When you load a new program, say, a web browser, you are simply feeding a new, complicated set of data. The machine description no more onto the universal machine embodder.
The same physical chip simulates a completely different conceptual machine.
That ability to treat code as data is the reason your smartphone can run millions of different apps without you needing to physically redesign it every single time you download one.
The synthesis is complete.
It is.
We've shown that the simple tape and head of the Turing machine are computationally equivalent to our theoretical software model, MiniPy. They define the exact same class of functions.
The Turing computable functions.
And that is the full scope of the Church-Turing thesis. The primitive, simple Turing machine has the full computational strength of any real modern PC. The difference between complex hardware and complex software it dissolves.
It dissolves into a single, fundamental mathematical process. The manipulation of symbols and bits according to a finite set of rules. And that means we can now study the limits of computation using this simplest possible model and know that our results apply to everything, from a pocket calculator to, well, maybe even a quantum computer, as long as that quantum computer is still constrained by the finite rules of formal logic.
So let's wrap up these core takeaways for you, the learner. We've not just analyzed some historical machine today. We've really defined the mathematical soul of every single machine you use.
Right. First, the foundation. The Turing machine is the fundamental, minimal model of computation. It just abstracts away all the physical limitations of the von Neumann architecture, and it leaves us with this pure conceptual machine that has infinite memory but finite logic.
Second, the equivalence. The fact that our MiniPy programs can be perfectly mapped onto these multi-track TMs really proves the power of the Church-Turing thesis.
It does. It shows that complex software logic, like a while loop or binary math, is fundamentally just a sequence of simple, repetitive state transitions and symbol manipulation on a tape.
And third, the universal machine. The universal machine, Love-Agoda, is the absolute foundation of all modern computing. It proves that a single piece of fixed hardware can simulate any other logical machine just by reading the program's description, the code, as another form of input data. We have spent all this time defining what is computable, what a machine, given enough time and tape, can actually solve. But the theory doesn't stop there.
No.
If we've defined the full strength of the computer, the logical next step is to find its weakness.
Exactly. The ultimate question of theoretical computer science now presents itself. Are there functions, are there problems that are fundamentally, mathematically, and permanently unsolvable?
Unsolvable by any computer, whether it's the simple TM or the most complex supercomputer we could ever build.
By any computer.
That seems counterintuitive. If we can define the full power of computation, shouldn't every problem fall somewhere within that scope? I mean, how do you prove the existence of something that doesn't exist?
You use a powerful, elegant, and almost devious mathematical proof method that was devised long ago by Georg Cantor in set theory, and then famously adapted by Alan Turing for computation.
Diagonalization.
Diagonalization. It requires us to understand countability and enumerability. The fact that we can, believe it or not, systematically list or enumerate all possible Turing machines and therefore all possible programs.
So we'd have to show that the set of all possible problems is, in some sense, larger than the set of all possible programs that could ever be written to solve them.
Precisely. If we can make a list of every single Turing machine, M$, M2, M33, and so on, forever, we can then use that list to construct a very specific problem, let's call it PDD-DO, that is guaranteed not to be on that list.
And if PDDO is a real, well-defined problem, and no machine on the list of all possible machines can solve it,
then we've found a truly unsolvable, non-computable problem.
a logical hole in the fabric of mathematics that will remain unsolvable for all eternity. We are now prepared to search for the boundaries of knowledge itself. That is quite the mission for next time. Thank you for guiding us through the profound mechanics of the Turing machine.